All right, so moving on to our next set of reactions, this is now going to be alpha carbon alkylation, right? So sticking an alkyl group on that alpha carbon. In terms of mechanism, these are probably one of the easier ones, right? Because all we're really doing is first using LDA. What does LDA do it for us? That creates our enolate ion. And then you're just going to take this enolate ion and react it with an alkyl halide, right? So you're going to have, I don't know, something like this. Some alkyl halide. Your enolate ion is just going to be a nucleophile and kick off that leaving group there. Okay, so this is just sort of an SN2 reaction, nothing crazy going on here. Yeah, and so because it's an SN2, typical restrictions apply. We'll work with secondary alkyl halides, although the E2 product will dominate. Really won't work with tertiary alkyl halides at all because you'll only get E2 product. Yeah, so, but now let's talk about regioselectivity when we have an unsymmetric ketone, because that's actually going to be the meat of what's difficult about these alkylations. When we have an asymmetric ketone, so for example, this one has this R group here. Let's just make it easy and make it a methyl group. You have two different enolate ions that could form, right? And this is, of course, the resonance contributor where the negative charge is on the oxygen, and there's that double bond there. So this illustrates what's going to be the crux of the regioselectivity of this kind of ketone, of this kind of reaction. Here you have the more stable, more substituted enolate ion, right? So this is going to be the thermodynamically favored one because it's just more stable, just like our normal rule for alkenes. The more highly substituted they are, the more stable they are, right? So this is the more stable enolate ion. However, this one is the kinetic enolate, right? It's going to form the fastest because it would require removal of an alpha hydrogen from this carbon right here, which is less sterically hindered. So although the other enolate ion is more stable, this one's less stable, but it forms faster, right? So this is now our second, I think our second time that we've seen this idea of a thermodynamic product and a kinetic product, okay? So we would expect the thermodynamic product to form at high temperatures and the kinetic product to form at low temperatures, okay? And so that's sort of exactly what we're going to see here. This is just an illustration using a free energy diagram, right? So our kinetic enolate, it has the lower lower activation energy, but it's also less thermodynamically favorable, a higher free energy, compared to the thermodynamic product has that higher activation energy, but a lower free energy. Okay, so that means that depending on the temperature, we'll get substitution at different locations, right? At lower temperatures, we'll get substitution on the less highly substituted carbon. And at higher temperatures, we get substitution on the more highly substituted carbon. Okay, so these reactions depends on where the temperature that you carry them out at will dictate where the incoming, which alpha carbon the incoming reagent goes to. Now, another way that kind of, in a way, makes it easier, in a way is just another thing you have to remember about this, is we actually use different bases at different temperatures. LDA is the choice to use at low temperatures. This was one of our strong bases we talked about was good. And at higher temperatures is when we use the sodium hydride, okay, or room temperature, higher temperatures though. So anyway, so the choice of base is going to actually depend also on whether or not you want the kinetic product or the thermodynamic, right? And so again, low temperatures favor the kinetic product, high temperatures favor the thermodynamic product. Okay, so there's some regioselectivity to these alkylation reactions. There's two other alkylation reactions that we're going to talk about that are kind of special. The first one is called a malonic ester synthesis. And that's because a key player is going to be this guy here, which is diethylmalonate. Okay, what that's going to do for us is turn an alkyl halide into a carboxylic acid. Notice that we have 2 additional carbons in our carboxylic acid as well. All right, so let's look at the mechanism here. We're going to take our diethylmalonate. What do we know about these 1,3-dioxos and their alpha hydrogens? They're particularly acidic. So that alpha hydrogen is going to be removed by an alkoxide ion, and that's going to generate this enolate ion here. We call these stabilized enolates when they're between 2 carbonyl groups. So when they're one of those 1,3-dioxos. And then just like we saw before, nothing really special, kind of exactly what you would expect. This enolate ion can react with the alkyl halide. It's going to be the nucleophile. The alkyl halide will be the electrophile, kick off that leaving group. And so now we're left with that R group on our diethylmalonate. Okay, so we could stop there if we wanted, but this is of course not the carboxylic acid that we were looking for. So the next step is going to be to treat it with acid. And what happens to an ester when we treat it with acid? We should know this from last chapter. The ester groups will turn into hydroxyl groups, right? This is just the Fischer esterification, or I guess the reverse Fischer esterification. But under acidic conditions, there's that equilibrium between carboxylic acid and ester. Okay, so this gives us this sort of dicarboxylic acid here. And then the last step is we're going to heat this dicarboxylic acid, and it's going to break apart into CO2 and just one carboxylic acid, right? So this guy stays here, and then this carbon turns into CO2. So we sever this bond right here. This is actually something that's a process that you can do for any, it doesn't have to be this dicarboxylic acid. I guess it would be a 3-oxo carboxylic acid can undergo decarboxylation, which is a loss of CO2. Okay, so it doesn't have to have 2 carboxylic acid groups like it does here. It can be any 1,3-carboxylic acid, or I'm sorry, any 3-oxo carboxylic acid. So any carboxylic acid where you have an oxo group 1, 2, 3 carbons away. So it doesn't really matter what's going on back here. All right, and we'll see what happens here. Again, this is called decarboxylation, the loss of CO2. So what happens is the pair of electrons from your oxo group, your oxo group, your carbonyl group, comes up and grabs that hydrogen from the carboxylic acid tip. And that kind of does this sort of pericyclic type reaction where that pair of electrons comes down, but carbon can't have more than 4 bonds, so kicks that over as well, right? So this is this pericyclic type reaction that kicks off CO2. And this is, again, the carbon that's part of the CO2. And these are the 2 carbons that are going to remain attached to that R group. Actually, first we'll go to an enol, but we know that enols will tautomerize in favor of their keto counterparts. In this case, we got this OH group. But again, I kind of want to point out this OH group isn't really doing anything in this particular reaction. It's the 1 and the 3 oxo group and the carboxylic acid group that are really important. And so what we're left with is now a carboxylic acid that has, our original carboxyl or our original alkyl halide portion, as well as 2 additional carbons. Okay, so this is malonic ester synthesis. There's an analogous, Yeah, so overall, just to kind of hammer this home, you take your um, diethylmalonate, and that's this guy here, treat it first with strong base. That just creates the enolate ion. Then you add in your alkyl halide, and then by treating with acid and heat, you sort of cleave that guy in half. One half goes off as CO2, and the other half you're left with your alkyl halide attached. So this is this plus CO2. Okay, you can actually, you can repeat steps 1 and 2 up here twice in order to get 2 alkyl groups on your diethylmalonate, then treat that with acid and heat. And so you get this sort of di-substituted carboxylic acid, again, with an additional 1, 2 carbons. Okay, the last one, which I'm actually going to have you guys do the mechanism all by yourself because it's very similar to what we just saw, is instead of taking diethylmalonate, you're going to take what's called acetoacetate esters, and that is, basically the same thing, except for over here is not another ester. It's just an acetate, just a CH3 group. So taking this and treating it with base, what's that going to do? You're going to get your carboxylate ion. You're going to add in the alkyl halide, treat that with acid that will convert this to a carboxylic acid group. And then heat will again do that 3-oxo carboxylic acid decarboxylation. Okay, but this is a mechanism you guys are going to do all on your own without me showing you.